Hello everyone, this is Charan from Shiv Venkateswara College of Engineering. I'm here to speak about quantifying uncertainty in AIML. Welcome to the exploration of uncertainty quantification in AI and ML. Understanding and quantifying uncertainty is crucial for building reliable and trustworthy AI systems. This presentation will delve into fundamental concepts, methods, and applications of uncertainty quantification in the real of AI and machine learning. Introduction to uncertainty in AI and ML. Data uncertainty and model uncertainty. In data uncertainty arises from incomplete, noisy, or based data. This can lead to inaccurate predictions and biased models or outcomes. Techniques like data augment and robust optimization can help mitigate this uncertainty. Model uncertainty. Model uncertainty stems from the inherent complexity of the model and the limitations of the learning algorithm. This can lead to the overfitting or underfitting resolution in poor generation performances. Regulations and enzymal methods can help address the uncertainty. Sources of uncertainty in data and models. Data noise, missing data, model complexity, algorithmic behavior bias. In data noise, the data noise arises from errors in data collections, measurements, or processing. This can lead to the inaccurate model training and prediction. Techniques like outliner detection and data cleaning can help reduce noise. In missing data can lead to biased model training and inaccurate predictions. Imputation methods and data aggregation techniques can help addressing missing data and improve model reliability. In model complexity can lead to overfitting where the models learn and train data too well but fails to generalize to unseen data. Regulations, methods, and cross validations can help mitigate overfitting. And in the algorithmic bias can lead to unfair or discriminatory outcomes. Techniques like mechanic learning and bias mitigation strategies and can help addressing and promote fairness in AI systems. Probability theory and statistical methods. Probability distribution and statistical inference. In the probability distribution provide a mathematical framework for representing and quantifying uncertainty. They describe the likelihood of different outcomes based on available information. Statistical inference. Statistical inference allows us to draw conclusions about populations based on data from samples. It involves using probability theory and statistical methods to estimate parameters and test hypotheses. Bias in inference and uncertainty quantifications. In bias in inference and uncertainty quantification, there are pair distribution, likelihood function, posterior distribution. In pair distribution represents our initial beliefs about the unknowing parameters before observing any data. They reflect existing knowledge or assumptions about the problem. In the likelihood function quantifies the probability of observing the data given in a specific set of parameter values. It measures how well the data fits the model under different parameter choices. And in the posterior distribution, the posterior distribution represents our updated beliefs about the parameters after observing the data. It comes to information within the likelihood function and provide the more information on uncertainty. Sensitivity analysis and uncertainty propagations. sensitivity analysis Sensitivity analysis explores how challenges in input variable affect the output of model. It helps how to identify critical variables that contribute most to uncertainty in the predictions. And in the uncertainty propagations, in uncertainty propagations considers the impact of uncertainty in input variables on the uncertainty in the model's output. It qualifies how uncertainty is transmitted through the model calculations. And in scenario analysis, in scenario analysis involves exploring different possible futures scenarios by verifying input variables and observing the model's predictions under the different conditions. It helps access to the robustness of the model to various uncertainties. Uncertainty visualization and communication. Confidence intervals, probability distribution, and sensitivity plots. In confidence intervals, provides a range of possible values of for a parameter based on a specific level of confidence. And in the probability distribution, the probability distribution depute the likelihood of different outcomes, providing a visual representation of uncertainty. Applications of uncertainty quantification in AI and ML, medical diagnostics, self-driving cars, financial forecasting. Medical diagnostics. Uncertainty quantification helps access the reliability of AI-powered medical diagnosis, providing confidence in diagnosis and reducing the risk of false positive or negatives. Self-driving cars. Uncertainty quantification is essential for autonomous driving systems to make safe and reliable decisions in unpredictable environmentals. Financial forecasting. Quantifying uncertainty in financial forecasting helps investors make informed decisions by providing a range of possible outcomes and evaluating the risk associated with the different innovations. The limitations and challenges in uncertainty quantification: data availability, model complexity, and computational cost. In data availability, insufficient data can limit the effectiveness of uncertainty quantification technologies, making it difficult to accurately access models and uncertainty. Model complexity. Highly complex models can make it challenging to qualify uncertainty, requiring techniques and sustainable computational resources. And in the computational cost, uncertainty quantification methods can be com- componentally intensive, requiring single or timing, especially for complex models.